Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever feel like the things you measure don't quite line up with what is actually happening in real life? Like you are trying to catch a fast-moving car with a slow camera? Well, that is exactly the problem a team of researchers explored in a fascinating paper about timing in causal research. They call it temporal misalignment. Think about it like this. Imagine trying to understand how quickly stress builds up during your workday, but you only measure your stress levels once in the morning. And once at the end of the day, you are missing all the ups and downs in between. This study dives deep into how this timing mismatch messes with our understanding of cause and effect, especially in psychology and social science research. So, what is the big deal about timing in research? We often want to know if one thing causes another. For example, does stressing about a deadline cause you to procrastinate more? To answer this, we collect data over time. But here is the rub. The time between our measurements might not match the time it actually takes for things to happen. The researchers call this temporal misalignment. It happens in two main ways. One is systematic undersampling, where we don't measure often enough. The other is time aggregation, where we average measurements over a period, like asking you how anxious you felt last week instead of right now. The paper's authors simulated different situations where this timing mismatch happens and showed how it can lead to really skewed results, even making it look like there is a cause and effect link when there isn't, or hiding one that actually exists. The researchers wanted to see how this timing problem affects our understanding of cause and effect in studies that follow people over time. They looked at two very common things researchers want to know: lag -0 effects, which are like immediate, right now effects, and lag -1 effects, which are the effects from one measurement point to the next, kind of like yesterday's influence on today. They used computer simulations to create scenarios where the data collection timing was off, either by not measuring often enough or by averaging the results. Then they used different statistical tools to analyze this misaligned data. What they found was pretty striking, even when there was no real effect happening in their simulated data. Their analysis suggested there was one. This happened because the timing of the measurements didn't match the timing of the actual process they were trying to study. It is like trying to judge a race by only looking at the start and finish lines with no idea what happened in the middle. So let's break down how they explored this. Imagine you are tracking how much you exercise and how happy you feel over several weeks. If you only record your exercise and mood once a week, you are undersampling. If you were to ask yourself, how much did I exercise on average last week? You are engaging in time aggregation. The researchers point out that most of the time, these timing issues are just assumed away, meaning researchers don't explicitly think about them. But this paper argues they're super important, especially when we want to claim something causes something else. They highlight that a lot of behavioral changes happen much faster than we typically collect data, leading to this gap, this misalignment between the real world process and our measurements of it. Let's dive into undersampling. Imagine a process that changes very quickly, like your mood after getting good or bad news. If you only measure your mood once a day, you are going to miss a lot of the nuances. The researchers explain that when we undersample, the relationships we see in our data can become weaker, or even seem to disappear. For example, if a true effect is supposed to happen over a short period, but we only measure after a long interval, that effect gets diluted. The paper uses mathematical ideas to show that, for example, an autoregressive effect, that is just how much a variable influences itself, over time gets smaller and smaller as the time between measurements increases. This means that if we're not careful, we might conclude there's no real connection happening. Now, let's talk about time aggregation. This is when we average things out. Think about asking someone about their anxiety levels over the past week instead of their current anxiety. While this can sometimes smooth out noise, it also changes the original pattern. The authors point out that this kind of averaging can make it harder to see the true dynamics. They even mentioned that early researchers in economics who aggregated things like stock prices, noticed that it made the data behave differently. The paper suggests that when we aggregate, the relationships we observe can be qualitatively different from the original, fast-moving process. It's like trying to understand a symphony by only listening to the average volume over broad sections. You lose the melody and the rhythm. To really test this, the researchers ran a big simulation study. They created a digital world where they could control exactly how things happened and then deliberately messed with the timing of the measurement. They set up 5 different scenarios that represented common research situations. In scenario 1, they imagined a situation where the cause, let's call it an intervention, like a new app feature, was something that only happened at specific measurement points. But the effect, say user engagement, could change much more rapidly in between those points. This is like when an app sends you a notification But your engagement with the app can fluctuate a lot during the day. They found that even when the timing of measuring engagement was off, the immediate lag -0 effect of the notification was still estimated pretty accurately, as long as the intervention itself was randomly assigned and didn't depend on anything else. Scenario 2 got a bit more complicated. Here, the intervention X wasn't just random. It could be influenced by previous levels of the intervention or the outcome. Yeah, I think of a situation where your previous sports performance influences your decision to play again, and your previous self-esteem also plays a role. They found that when the timing was off in this scenario, things got really messy. Even when they used more advanced statistical tools that looked at both variables together, the estimates for both the immediate lag -0 and the next wave lag -1 effects were biased. This is a crucial point. Even controlling for previous measurements wasn't enough to fix the problem when the underlying timing was matched. This scenario is where it really starts to unravel. Here, both the cause X and the effect had this timing mismatch. Imagine something like social media use and anxiety. Both can change rapidly, and if you are only measuring daily, you are missing a lot. The researchers simulated this by having both variables change frequently and then only taking measurements at much longer intervals or averaging them. The results were dramatic. The bias in estimating causal effects became much worse. For the immediate lag -0 effects, the estimates were way off. And the chance of mistakenly concluding there was an effect when there wasn't what they call inflated type I error rates, shot up astronomically, especially with the multivariate models that try to account for more complex relationships. Now, things get even more realistic. Scenario 4 added a time varying confounder, something that influences both the cause and the effect, and also changes over time. Think of something like alcohol consumption when studying the link between social stress and mood. Alcohol use can change daily and affect both stress and mood. The researchers found that while this third variable did add some complexity, the main driver of the bias was still the timing mismatch in the primary cause and effect variables X and Y. Even when they tried to account for this time, varying confounder, the underlying temporal misalignment, was the bigger problem. Finally, they looked at a scenario mimicking panel data. This is the kind of data you get from large surveys that ask people the same questions, maybe once a year. The measurements are far apart, and the questions themselves often ask about past periods, meaning there is both undersampling and aggregation. Think of annual surveys asking about monthly social media use. Using this kind of data, they observed similar patterns. The lag -0 effects were massively overestimated, and lag -1 effects, which are usually the focus in these studies, became incredibly small and often disappeared entirely. This suggests that when we use this type of data, we might be missing or completely misinterpreting causal relationships. So, what does all this mean? The big takeaway from this paper is that temporal alignment, making sure your measurement timing matches the timing of the actual process you are studying, is crucial for causal research. When it is off, even with sophisticated statistical models, your estimates of cause and effect can be wildly inaccurate. They found that in most non-experimental situations where the cause isn't randomly assigned, temporal misalignment causes serious problems for both immediate lag -0 and next wave lag -1 effects. Interestingly, they noted that the bias for lag -0 effects was often worse than for lag -1 effect. This is partly because lag -1 effects can become so small with long measurement intervals that any bias becomes less noticeable in absolute terms. Now, every study has its limits, and this one is no different. The researchers use specific types of simulations and statistical models. They acknowledge that real-world data can be even messier. For instance, how people recall their past experiences for aggregated measures might be different from a true mathematical average. They also point out that their simulations focused on specific ways variables influence each other, and other types of causal relationships might behave differently. However, the core message about timing seems to hold. They also emphasize that this isn't just a modeling problem. It is a fundamental issue of identification, meaning that even with perfect data, if your timing is off, you might simply be unable to uncover the true causal relationship. Given these challenges, what can we do? The paper suggests a few directions. One is to use continuous time modeling. This approach tries to model processes as if they were happening continuously, even if we only measure them at discrete points. It is like trying to draw a continuous line through a few scattered dots. This could help us understand faster processes better, Even with infrequent measurements, another idea is to collect data at varying time intervals, both within individuals and across people, which might give us more information to work with. They also mention advanced techniques from causal inference, like inverse probability weighting, which aim to correct for missing data points or unmeasured confounders. But these require a lot more research to be widely applicable. The field of machine learning also offers some algorithms that try to learn causal relationships from undersampled data, but these also have limitations. So, to wrap it all up, this paper is a really important wake-up call for anyone doing longitudinal causal research. Temporal misalignment, the mismatch between when things happen and when we measure them, can seriously undermine the validity of our findings, whether it is by not measuring often enough or by averaging our data. We risk drawing the wrong conclusions about cause and effect. The researchers stress that we need to be much more mindful of timing when designing studies and analyzing data. Moving forward, we desperately need better statistical tools that can help us navigate these timing challenges when perfect alignment isn't possible. It highlights that understanding the when is just as critical as understanding the what and the who in psychology research. From my perspective, this is a critically important paper that shines a light on a subtle but pervasive issue in psychological research. The authors do an excellent job of demonstrating, through simulations, just how badly temporal misalignment can distort our understanding of causal relationships. The fact that even sophisticated multivariate models can be fooled by this timing mismatch is a stark warning. What I find particularly compelling is how they connect these complex statistical issues to relatable concepts like stress, anxiety, and social media use. It makes the abstract problem of temporal misalignment feel very real. The simulation results, especially the dramatic inflation of type I error rates in scenario 3, are a powerful illustration of how we might be fooled into believing a causal link exists when it is just an artifact of our measurement timing. The limitations they mention are fair. Real human memory and recall are imperfect, making aggregated self-report data even more complex than their ideal mean aggregation. Also, the specific causal structures they simulated are simplifications of reality. However, the core problem they highlight, that processes unfold over time and our measurements might not capture that unfolding accurately, is universal. The implications for real-world applications are huge. If we're using data collected at slow intervals to inform interventions for fast-moving psychological processes, we might be making decisions based on flawed information. This could lead to ineffective or even counterproductive interventions. For example, trying to manage everyday anxiety with a once-a-month check. It might miss the crucial moments where a timely intervention could make the biggest difference. Future research absolutely needs to focus on developing and validating those continuous time modeling approaches and other causal inference techniques that can better handle the temporal dynamics of psychological phenomena. We need methods that don't assume a static snapshot but can truly capture the ebb and flow of human experience. What are your thoughts on this? Have you ever felt like your measurements weren't quite capturing the real story? Let us know in the comments below, and if you found this breakdown helpful, please give this video a thumbs up. Subscribe to RUBIN'S Mind Lab for more science explained, and hit that notification bell so you don't miss our next dive into the fascinating world of research. Thanks for watching.